Hello, I'm Ardra Suresh. I'm a postgraduate student working in Space Systems Laboratory under Dr. Sanat K. Biswas. My research work is Monte Carlo approach for collision probability estimation. Due to ever increasing space activities, there has been a stark increase in the number of space objects and debris, which include defunct satellites, pieces of space hardware, and launch vehicle remains. This poses a huge threat to every space mission planned and for existing active satellites. Hence, it is very crucial to determine the collision probability of active satellites with other resident space objects accurately to avoid a fatal collision. Now, the objective of our work is collision probability estimation with much better accuracy because a slight miscalculation can cause fatal damage to space assets. Now, the orbital data needed for this work, that is the position data and the velocity data of the space objects, is obtained from Space Surveillance Network in the form of TLE data or two line element set. And this data is used to create orbit objects. Now, TLE data can have inaccuracies because of the measurement inaccuracies. Now, there are various, what we can do is to mitigate this problem is to create various possibilities of orbit object positions by sampling the orbital element values to a large data points. This approach is called Monte Carlo approach. Now, this is done for both primary and for secondary objects. Primary object is the active satellite, and the secondary object are other objects and space debris. This is a much accurate representation of the uncertainty of the orbits. Coming to the implementation part, here basically what we do is we use the mean and standard deviation of the data obtained from the TLE. Using this, sample points are created for the orbit object of the space objects and space objects. That is, from the block diagram we can see that the TLE data is imported. The primary object orbital parameters are generated. Similarly, for the secondary objects, the orbital parameters are generated. Using that, the apogee and perigee height is calculated to generate to work the apogee perigee filter. Now, after apogee perigee filtration, we can remove a certain number of objects from our consideration, and then these are used to create the sample points. These sample points are then propagated to the future by considering the perturbations. After that, after propagating, we get the relative velocity and position values of the primary with respect to the secondary. These values are then used to calculate the covariance matrix. From the covariance matrix, we can generate the PDF, probability distribution function. After that, we consider a warning box around the objects. This around a space object, we consider the warning box. Now, if an object is coming inside the warning box, that probability is calculated, and that is a collision probability. For object pairs with collision probability above a certain threshold, it is then shortlisted, and their miss distance, the epoch value, and the time of closest approach is calculated and tabulated in the form of conjunction data message or CDM. Also, for better understanding of the orbits, a 3D visualization of the sample points of the orbits is important. So, all the sample points generated are also visualized in 3D. We are actually working on a better orbit visualization method as a future work. All this, as you can see in the results, all this implementation was done in the Python, in using a Python code. Now, one space object with NORAD cat ID 43212 is considered as the primary object, and others are considered as secondary objects. Now, using taking this consideration, all the results were generated. The miss distance, the epoch value, and collision probability at the time of closest approach for the secondary objects with high chance of collision is calculated, and that is generated as a conjunction data message. Also, the plot generated is inter-satellite distance with time. The inter-satellite distance is actually the distance between two satellites, that is the primary object and the secondary object. Now, inter-satellite distance for two objects become very close, become small, that is at the time of closest approach they come the nearest, and then they move apart, and this repeats. This keeps on repeating actually. This is how inter-satellite distance change for any two objects in space. Now, a collision event is more likely when the inter-satellite distance is less, right? So, that is when we need to find the collision probability and the CD. Now, coming to the conclusion part, we check the inter-satellite distance, and from the inter-satellite distance we get the missed distance. That the time missed distance is the time distance at the time of closest approach, and that is the point where the collision event is most likely to happen. We calculate the collision probability. Now, for getting a much better accuracy at this point, we generate the sample points. The sample points of the orbit object at various probable locations of the orbit based on the available TLE data is generated. And this is then used to create the orbit objects. When all probable locations are considered, it increases the accuracy of the calculations. For a particular primary object, a list of secondary objects with high risk of collision and the CDM is generated. This information can be found out for any object in space and using the same program, and the detailed results can also be obtained. Thank you.